This video is about designing a voltage divider. It corresponds to the example in section 5.1.1 of the Applied Analog Electronics textbook. Now, design is really what this course is about, not analysis. And so this example is more typical of the sort of work you'll be doing in this course than a number of other things we might have done. Okay, let's take a look at what the problem is we want to solve. We are going to be given a voltage source, and I believe for the book I picked 3.3 volts. We're going to be given a desired output, 1.8 volts. And furthermore, we're going to be given a constraint, and that is that the entire circuit cannot take more current than 30 microamps. Now, notice that this constraint is an inequality, not an equality. And that's a very important thing to remember to keep in mind, that constraints are inequalities. And you should always represent them that way, because when you manipulate them, move things around, move things from one side of the inequality to the other, you have to keep track of which direction it points. And if you try and do it as an equality, two things will go wrong. One is you might get confused about whether that's the minimum or the maximum you're allowed. And the other thing is that you will try to go always right to the edge of your constraint. And that's usually bad design practice. Nearly always if somebody says no more than 30 microamps, you're going to be much safer. You say, oh, well, I'll only use maybe 10 or 15 microamps and not get anywhere close to the constraint. So usually constraints are, this is the edge of danger. You don't want to go that far. And so you never want to design to try and get right to that edge, because then you've got a very fragile design. So constraints should always be taken as, okay, stay away from the constraint. Don't try and solve it to equal the constraint. You don't want it to equal. You want it to be much less than, or at least somewhat less than if the constraint is too difficult to meet. Okay, so we've only got one circuit. All we've learned is one circuit. Use that circuit. And incidentally, in this class, a lot of times when you can't figure out what it is you need to do, the answer is try a voltage divider. Voltage dividers are very versatile circuits. We'll use them for a lot of stuff. All right, so there's our circuit. Something missing? We don't have any component values for these two resistors. And to get this thing to work, we need to choose those component values. So we have RU and RD here, and we don't know what they are. Two unknowns. Well, what do we have? Well, what does this current constraint tell us? If this is a voltage divider, and we do have a constraint here that we're not allowed to take any current out of that voltage source. So we can't take any current from the 1.8 volts. That means that the current here and the current here are the same, and that's the total current that the circuit uses. All right, what is that current? Well, we can just take Ohm's law here and say the current is 3.3 volts divided by RU plus RD. And we also know that that current's got to be less than 30 microamps. So we can turn this constraint around. Multiply both sides by RU plus RD, divide both sides by 30 microamps, and get RU plus RD is greater than 3.3 volts over 30 microamps. And here you can see the advantage of having kept this as an inequality is I know that the resistors have to be at least this big. Well, how big is that? Let's get out a calculator. And try putting in 3.3 volts and dividing by 30 micro is 10 to the minus 6, 30 microamps, and I'll get that that has got to be 110 kiloohms. Okay, so I need at least 110 kiloohms for the sum of these two resistors. And larger would probably be better because that would reduce the amount of current we're taking. Okay, that tells us sort of roughly how big them are, but it doesn't tell us how big is RU, how big is RD. So let's look at what we know about I. We know that I is 3.3 volts over RU plus RD. But we can also look at just this single resistor here on the bottom and say, well, that's 1.8 volts over RD. And it's also, well, how much voltage is there across RU? We have 3.3 volts minus 1.8 volts. That's 1.5 volts. So we have 1.5 volts over RU. So this tells us that RU to RD is going to be a 1.5 to 1.8 ratio, just in order to get having the same current. What values can we pick? Well, let's go and take a look at what values we might have available. In the book, there's this chart of what the E6, E12, E24 series are. And we're looking for a pair of values in here that have a ratio of 1.5 to 1.8. Well, if we look at the E12 series, that's very simple. We have 150 and 180. All right, so let's go back to here and say let's use 150 and 180. So if we make RD be 180 and RU be 150, then 1.5 volts over 150, 1.8 volts over 180, same ratios. But how big are these? And notice I haven't put units on these things yet. That's just sort of scaling factors. I need them to add up to more than 110 kiloohms. Well, if I just made this 180 kiloohms and this one 150 kiloohms, then they would add up to 330 kiloohms. And if we had 3.3 volts divided by 330 kiloohms, I could do that in my head, but I get 10 microamps. So $10 microamps is definitely less than 30 microamps. We've made a constraint. So we have got our U being 150 kiloohms and RD being 180 kiloohms. Now, this isn't the only possible solution to this problem. For instance, I could have had each of these be 10 times bigger, and then I would have only gotten 1 microamp instead of 10 microamps. So that would be 1.5 megohms and 1.8 megohms. And in fact, there are other ratios that come very close to 1.8 to 1.5, because when we look at these ratios of numbers here, if we take any two adjacent numbers in the E12 series, they're going to be very close to that 1.8 to 1.5 ratio. And so there are many correct solutions to this design problem. And that's another very important fact to remember, that design problems rarely have one answer. If everybody in the class is getting the same answer, something's probably wrong, like cheating. Because there are lots of correct answers. And how good they are often depends on things that may not have been specified in the initial constraints. How important is it that this be small current? Less than 30 microamps? I got that. But is 10 microamps better, or is 1 microamp better? Do I care about what the output impedance is here, how much resistance there is basically in series with this voltage? Maybe, maybe not. And so quite often you have to look at, okay, I've got a lot of different design solutions here. The first one I come up with is not always the best one for the application, and you need to sometimes go and ask the person who originally asked you to design, well, I've got a couple different designs here. Here are the trade-offs. What other considerations did you not tell me about that might matter here? So keep that in mind when you're doing designs, is that quite often design problems as given to you will be under-constrained. There'll be multiple solutions, and you'll often have to make decisions about which solution is the most appropriate one based on information that you haven't been given.